Hi. So, we talk about divide and conquer paradox. So, this is a divide technique. This is an algorithm technique to solve the algorithm problem. So, it has basically 3 steps. First one is divide step. So, we have given a problem of size n. So, what we do in this step? We divide the problem into sub problems. We divide the problems into sub problems of lesser size. And next we conquer the sub problem by solving them recursively, that is the conquer step. We solve the sub problems recursively, and the last step is the combined step. So, in the combined step, so we have now solution of the sub problems. Now, to combine step, we combine the solution of the sub problems to get the solution of the whole problems. So, we combine the solutions of the sub problems to get the solution of the whole problem or the original problem of the whole problem. Okay, so this is the basically the steps. So, let us take an example. So, we have seen the merge sort. So, in merge sort what we are doing, we have given an array of size n and we need to sort it. So, this is a problem of size n, it is a sorting problem. So, what we are doing, we are going to the middle of the array and we divide the array into 2 sub arrays. Now, we recursively sort, so that is the divide step. Now, we recursively solving this sub array and this sub array, that is the conquer step. Now, once we have the solution for solution of this, once these 2 sub array is sorted, then we are combining by calling the merge subroutine, which is linear time algorithm, to have a sorted array, total sorted array. So, divide step is trivial in the merge sort. Conquer step is we are solving these 2 sub array recursively, and then combined step is basically the merge subroutine, that is we have 2 sorted array. Now, we are calling the merge subroutine to get to sort the array. So, now we have got the recurrence of the merge sort, which is basically T n is equal to 2 T n by 2 plus theta of n. So, this 2 is basically denoting the number of sub problems, and this n by 2 is denoting the size of the sub problems, and this is the cost for divide and combining, both for the divide and combine step. Okay. And now, we know how to solve this by master method. This is basically theta of n log n. Okay. So, now we talk about some other divide and conquer algorithm. So, the next one is binary search. So, in binary search, what is the problem? Problem is we have given a sorted array and we need to find out an element in the array, whether if it is there we will return that element, otherwise we say no. So, we need to find an element in a sorted array. This is the problem. So, how we can use the divide and conquer technique here? So, we have a sorted array, say for example 3, 5, 6, 8, 9, 10, 11. Suppose this is our given array. Now, suppose we are going to find whether 9 is there or not, that is our x. We are trying to search the element 9 in this sorted array. So, what we do? So, we first check in the middle. So, this is 1, 2, 3, 4, 5, 6, 7. So, we check in the middle. So, middle is basically this one. So, A4. So, we check with A4 whether A4 is matching with x or not. If not, we will check it is not matching. So, we are not lucky. So, we check whether 9 is greater than this middle or not. If it is greater than, so we will look at the right sub array. We will again search in the right sub array. Now, if it is less than, we will look at the left sub array. So, that is the divide step, and in the conquer step we will be recursively looking at that sub array, and then so 9. So, we will go for here. So, then we will check with this, it is less than. So, we will look at the left sub array of this sub array. So, it is 9. So, matching done. So, this is the divide and conquer algorithm. So, now what is the recurrence here? This recurrence is basically we are dividing the problem into, basically we have one sub problem. We are not looking into both the sub arrays, we are looking into one sub array. So, this is basically 1 t n by 2 plus the cost we are spending for divide and combining. So, that is basically theta of 1, constant time we are spending. So, again by master method we can see this is basically theta of n. So, this is a logarithmic algorithm for finding an element in a sorted array. Now, the next problem is powering a number. Okay, so we want to find out a to the power n, where n is a natural number. Say n could be 1000, n could be 100, something like that. So, we want to find a to the power n. So, this is the problem, a and n are given. So, we want to find a to the power n. So, how we can do? So, naive approach is, so we can multiply a. So, n minus 1 times. So, that will give us a to the power n, but the time complexity of that is basically order of n, because we are doing n multiplication. Now, we want to see whether we can use the divide and conquer algorithm to solve this problem. Okay, so, for that we need to write the recursive form of this. A to the power n can be written as a to the power n by 2 into a to the power n by 2 if n is even, otherwise a to the power n minus 1 by 2 into a to the power n minus 1 by 2 into a if n is odd. So, this is basically our divide step. So, we have a problem of size n, we are going to find out a to the power n. We divide the problem into two sub problems, basically we calculate this once. So, a to the power n by 2, once we have this solution of this sub problem, that we will do in the conquered step, then we multiply it twice, we get the solution of the whole problem. So, what is the recurrence? Recurrence is, so we are just computing a to the power n by 2 or this once, and then in the combined step we are just multiplying, if it is n is odd, we are multiplying this again with n. So, this is basically so this is the size of the sub problems. We are only computing one sub problem, one a to the power n by 2, and then this is the cost for divide and conquer. I mean the conquer combine, divide and combine. So, combine phase is basically we are multiplying two numbers. So, that is the same as binary search recurrence. So, the solution is this again by the master method of case 2. Okay, so, the next problem is finding the nth Fibonacci number. So, finding nth Fibonacci number. So, what is nth? What is the first Fibonacci number? We start with 0, 1, then we add this to 1, 2, 3, 5, 8 like this. So, this is we can say 0th Fibonacci number, or yeah. So, the form is this: if n is equal to 0, if n is 0, we can say starting with f0, 1 if n is 1, and other than this we have n minus 2 plus, this is the recursive form of the Fibonacci number. Okay. So, now the question is how we can find the nth Fibonacci number. N is another n is the, say we want to find thousands Fibonacci number, f thousands. So, how we can do that? That is the problem. Okay. So, one way is naive approach is what? We can just keep on calculating the Fibonacci numbers. So, like this, and ultimately we will go to the Fn like this. So, we will keep on calculating the Fibonacci number and we store the last two Fibonacci number, and then we get the, by adding this two, and we get the next Fibonacci number. So, what is the time complexity for that? Is basically order of n. So, now we want to see whether we can use some divide and conquer approach to solve this problem, to finding nth Fibonacci number. Okay. So, for that we know that nth Fibonacci number can be written as phi to the power n by root 5, where phi is the golden ratio, which is basically 1 plus root 5 by 2. So, 1 root of that. So, that is golden ratio, this is also called golden ratio. Now, if we can compute phi to the power n, then we can get the nth Fibonacci number. But this is looks like a powering a number, but here we are dealing with the real numbers. So, we have to see that how we can do the rounding the error. So, all those issues will come. So, this is not realistic approach to get a log n time complexity. So, we will look at a different method which is coming from this formula. So, f n plus 1, f n minus 1, this can be written as, so this can be written as 1 1 1 0 to the power n. So, this is a theorem where f n is denoting by the nth Fibonacci number. So, we can easily prove this theorem by induction. So, base case is n is equal to 1. So, for n is equal to 1, this is basically f2, f1, f0. So, this is nothing but 1 1 1 0. So, this is true for n is equal to 1. Now, we assume this is true for n is equal to k. So, that means f k plus 1, f k minus 1, This is basically 1110 to the power k. Now, this is our induction hypothesis. Now, we have to prove that this is true for n is equal to k plus 1. Okay, so for that we can just use this. So, k plus 1. So, k plus 2 f k plus 1 f k plus 1 f k, this can be written as f k plus 1 f k f k f of k minus 1 f of k minus 1 into 1110. This we can easily check. Now, for this we are using the induction hypothesis. So, this is 1110 to the power k and this is 1110. So, this is basically 1110 to the power k plus 1. So, the result is true for n is equal to k plus 1. So, by the method of induction we can say that result is true for all n. So, this theorem is true. Now, once this theorem is true, now to find the nth Fibonacci number, basically we have to compute this a to the power n, where A is this matrix. So, it is just a 2 by 2 matrix. So, this is same as powering a number, powering a matrix, but this matrix is a constant matrix. So, we can easily use that recurrence for this power similar to powering a number, and we can solve it by log n time. So, this is the divide and conquer technique for this problem. Okay. So, next we will talk about the matrix multiplication problem, and we can see how we can use the divide and conquer approach for that. So, okay, so suppose we have given two matrix A I J n cross n, both are n cross n. And we have a C matrix which is basically their multiplication. So, C is also n cross n matrix C I J. Now, we know C I J is basically summation of A I J, A I K, B K J. K is equal to 1 to n. This is basically the, we take the ith row of A, jth row, jth column of B, and then we do the inner product. So, how to get Cij? We can have the standard pseudo code for this. So, we are starting from I 1 to n, then j 1 to n, okay, and then we take this 0, and then we can have k 1 to n. Cij is basically Cij plus Aik into Bkj. That is it. So, this is the code. This is the standard code for matrix multiplication. And what is the time complexity for this code? We have 3 for loops, each of size n. So, the time is order of n cube. So, this is the time for matrix, standard matrix multiplication formula, matrix multiplication code. Now, the question is whether we can do some divide and conquer algorithm here or not to improve this time complexity. So, for that what we do? We just divide the matrix into sub matrices A, B, C, D and B, E, F, G, H. So, this is, each of these is just n by 2 cross n by 2. This is just the sub matrices. Okay. Now, C we denote R, S, T, U. So, this is also sub matrices. So, basically R is basically what? R is basically AE plus BG. S is basically AF plus BH. T is basically C plus dg, and U is basically this into this. So, Cf plus dH. Okay. So, this is the divide step. So, we divide the problem into sub problems, because this matrix multiplication of size lesser size, earlier it was a n cross n matrix, now this is n by 2 cross n by 2 matrix. So, we reduce the problem into sub problems. Here size is n by 2 cross n by 2. Now, how many matrix multiplication are there? So, there are 1, 2, 3, 4, 5, 6, 7, 8 matrix multiplication, and how many addition is there? 4 addition. So, what is the time complexity? Now, in the conquer step we will recursively solve these sub problems, and then once we have solution these sub problems, in the combined step we will just do the addition. So, this is basically we have 8 matrix multiplication plus the cost of the addition. We are having 4 addition, but each addition takes how much time. So, this is basically n cross n by 2 cross n by 2 a matrix P matrix plus a Q matrix. So, n by 2 cross n by 2. So, this will take order of n square time, because basically this is a vector. So, we are doing the position wise addition order of n square. So, this is basically order of n square. Okay. So, this is basically, if we apply the master method, this will give us order of n cube, which is not better than the standard matrix multiplication. So, the question is how we can improve this. So, idea is, so this idea is from Stresson's idea is, so here we are doing 8 multiplication, instead of 8 multiplication, if we can reduce just 1 multiplication, just 7 with a more addition. So, addition cost will be taken care by theta of n square. Suppose we are, instead of 4 addition, if you are doing 50 addition, 20 addition, that will be coming under theta of n square. So, that then in that case the time complexity will be reduced like log of 7 base n to the power, which is better than n cube. So, we will discuss the Stresson's idea. So, how Stresson is able to reduce the multiplication than addition. So, for that Stresson is computing some intermediate terms. So, P2 is basically 7 terms, P4 is B into G plus G minus C, P5 is A plus D into E plus H, P6 is B minus D to G plus H, P7 is A minus C into E plus F. Now, R is basically P5 plus P4 minus P2 plus P6, S is P1 plus P2, T is P3 plus P4, U is P5 plus P1 minus P3 minus P7. Okay, so this is the intermediate term. So, we have to, we can verify this, we can verify just R here, then it can remaining thing you can check whether this is okay or not. So, what is P1? R is basically it is telling P1 plus P2. Now, what is P1? P1 is basically this one. So, AF minus AH plus P2 is AH plus BH. So, this is basically AF plus BH, which is basically AF plus BH, which is basically S. So, you can just verify this is working fine. So, remaining term you can just verify. So, this is the idea. So, look at here, we are just doing the 7 multiplication to get this value P1 P2 up to P7, but we are having more addition. Here we are all the addition, subtraction is basically addition. So, how many addition? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 this is minus 15 16 17 8. So, we are having 18 addition, but we could able to reduce the multiplication by from 8 to 7. So, that is the idea. So, that way, so what is the time complexity? So, time complexity is basically the recurrence we got here is T n is equal to, so 7 multiplication, we reduce the problem into sub problems, and how many sub problems? 7 sub problems. Now, we recursively solve those sub problems, and then we have this combined step to get the solution of the whole problem. So, this is basically, so 18 addition, but that will be taken care by this part. So, this is basically by master method, this is the case 1. So, this is log of n to the power log of 7 base 2, which is n to the power 2.81, which is much more better than n cube. So, this is the idea of stations. So, this is the stations idea. Okay. So, so this is another example of divide and conquer algorithm. So, we can solve this matrix multiplication problem with the help of divide and conquer algorithm. So, in the next class we will be talking about another divide and conquer algorithm, which is quick sort, and we will see some version of the quick sort. So, we stop now. Thank you.